We are now going to talk about quantitative analysis of organic compounds. Here we will be learning about how to determine percentage composition of each and every element in the organic compound. Let us start with estimation of carbon and hydrogen. Look at the experimental setup which is used for the estimation of carbon and hydrogen in the organic compound. What we need to do is take a mixture of organic compound and cupric oxide and heat it in this type of setup. You need to constantly circulate oxygen. Now, what happens is carbon becomes carbon dioxide, hydrogen becomes water. It is passed through two U tubes. First U tube is packed with a known mass of calcium chloride and the second one is packed with known mass of potassium hydroxide. When the mixture of carbon dioxide and water passes through this, all the water gets absorbed in the U tube containing calcium chloride and all the carbon dioxide will get absorbed in the U tube which is filled with KOH. We need to find out, this is the reaction which takes place. This is the hydrocarbon you have. It has X number of carbons and Y number of hydrogens. Then it will consume this many oxygen molecules to give carbon dioxide and water. This is the balanced equation involved in this reaction. The oxygen comes mostly from copper oxide and to some extent it comes from the oxygen we are circulating in the experiment. And the fate of copper oxide is copper oxide gets itself reduced to copper. Now, the carbon and hydrogen in the organic compound, as you know, have been transformed into carbon dioxide and water. Carbon dioxide gets absorbed in calcium chloride U tube and this carbon dioxide gets absorbed here. We know the initial weight of these two U tubes separately. So, from the difference in the weights before and after the experiment, we can find out what mass of water got absorbed here and what mass of carbon dioxide got absorbed in this particular case. From the difference in the masses, you get the mass of carbon dioxide and water, and from this you can find out percentage of carbon and percentage of hydrogen. How? I'll show you after this. Just look at the experimental setup once again. This mixture is being heated. What is the mixture? It contains a known weight of say m grams of organic compound, known weight of organic compound with some excess of copper oxide, oxygen being circulated. You have known mass of calcium chloride, U tube containing calcium chloride, its initial mass is known to you. U tube containing potassium hydroxide, its initial mass is also known to you. This is the reaction which is supposed to take place and then the substances get absorbed here. Now, let us look at the calculation part of it. How to calculate percentage of carbon? First, you remember the mass of organic compound. I told you we take known mass of organic compound. The mass of organic compound, let us take it as m. Mass of carbon dioxide which is formed, that is the difference in the initial and final and initial weight of the U tube containing KOH, that is m2, and m1 is the mass of water. Now, in that case, the percentage carbon can be obtained from this 12 m2 by 44 m into 100, that gives percentage of carbon. Here I told you m2 is the mass of carbon dioxide. So, the weight of carbon in m2 grams of carbon dioxide is 12 m2 by 44 and this divided by m into 100 gives percentage of carbon. In a similar manner, you can find out percentage of hydrogen. Here you need to have mass of water. So, 2 m1 by 18 gives mass of hydrogen. This divided by mass of organic compound into 100 gives percentage of hydrogen. So, this is how the calculations are done for percentage of carbon and hydrogen. Let us now learn about estimation of nitrogen in the organic compound. Estimation of nitrogen. The method, there are two methods we are going to discuss one by one. Number one is Dumas method. Dumas method, this is the experimental setup. I have drawn it to show you. See, this is the place where organic compound is placed. A known mass of organic compound is placed along with copper oxide. So, this consists of copper oxide as an oxidant and the organic compound which contains nitrogen. Now, this is being heated. This is being heated and this is a copper gauze. copper gauze. Right. We are heating a mixture of organic compound and copper oxide in a current of carbon dioxide. Now, here nitrogen is formed. All the nitrogen present in the organic compound is transformed into N2, and part of it will become oxides of nitrogen. Those oxides of nitrogen will get reduced by copper gauze into N2 again. So, a mixture of N2 and CO2 will pass through this tube. This is mercury lock, and then this is KOH. So, when the gas mixture containing N2 and CO2 rises above, all the carbon dioxide will get absorbed in the KOH. So, what reaches here is N2 gas. This is a graduated tube. This setup is called as nitrometer. It is called nitrometer. You can find out the volume of gas which is collected here directly. Okay. Remember, this is not a dry gas, it is a wet gas. You also have moisture. Okay. This is a wet nitrogen gas. I'll try to explain you the setup once again. Here you have a mixture of organic compound and copper oxide being used as an oxidizing agent, and then it is being heated in a current of carbon dioxide gas. All the nitrogen present in the organic compound becomes N2, and part of it becomes oxides of nitrogen. Those oxides of nitrogen are reduced to nitrogen by copper gauze placed in the path of the gases. See, CO2 is being constantly circulated to flush out nitrogen which is formed here, and then the two gases N2 and CO2 enter into this tube. There is a mercury lock so that this liquid does not enter into this, right. Then the two gases, when they rise above, all the carbon dioxide will get dissolved in KOH. What gets collected here is N2. And because it has a markings for volume, you can read out directly what volume of nitrogen is collected in the nitrometer. This is a tube, and the height of this bulb can be adjusted up and down, it can be made. Now, what you can do is, if you match these two levels, then you can assume that the pressure experienced by the liquid outside is equal to pressure inside. Are you getting it? The pressure outside will be equal to pressure inside. So, the pressure which is experienced by this layer is nothing but atmospheric pressure. So, we can say that the nitrogen which is collected here must be exerting equal pressure on the liquid inside. But then that is not purely pressure due to nitrogen, it is having contribution by moisture also. We need to apply Dalton's law. We need to find out Pn2, therefore Pn2 equals to P atmosphere, that is atmospheric pressure minus aqueous tension at that temperature. Using this formula, you can find out pressure due to nitrogen. You also know the volume of nitrogen which got collected here, and by using a thermometer, dipping it in the liquid, you can find out the temperature. So, you know P1, V1 and T1, then you can change it to STP conditions and find out the volume of nitrogen collected in this experiment at STP. From that you can find out mass of nitrogen. From the mass of nitrogen and the mass of organic compound you have taken initially, you can find out percentage of nitrogen in the organic compound. And remember, this method is applicable to all types of organic compounds. All types of organic compounds can respond to this type of test, and you can exactly find out the percentage of nitrogen. You need to know aqueous tension, and you need to know the pressure in the atmosphere at the time of experiment. I will show you the calculation part after this. Look at the calculation part now. Let us assume that the volume of nitrogen which is collected in the nitrometer be V1 ml. The temperature at which you are doing the experiment, let us assume it to be T1, and the pressure of dry nitrogen is P1. You know, please remember we got it from the difference between atmospheric pressure and the aqueous tension. Now, let us assume that the mass of organic compound you have taken for the experiment is m grams. Now, we need to find out the volume of nitrogen under STP conditions. We can use that formula of ideal gas equation P1 V1 by T1 equals to P2 V2 by T2. So, let us assume that V2 is the volume of nitrogen at STP. So, it is equal to P1 V1 by T1 into T2 by P2. Now, from that we get volume of nitrogen at STP, and from that you can find out weight of nitrogen. See, we know that 28 grams of nitrogen at STP will occupy 22,400 ml of volume. So, we can find out weight of nitrogen of volume V2 at STP. From the weight of nitrogen, we can find out percentage of nitrogen. Percentage of nitrogen is equal to weight of nitrogen divided by the mass of organic compound into 100. This is how we find out percentage of nitrogen by Dumas method. There are no exceptions. It is applicable to all types of organic compounds. It is possible to find out percentage of nitrogen. The next method for the estimation of percentage of nitrogen in the organic compound is by Geldahl's method. We have already discussed Dumas method. Now we are talking about Geldahl's method. Here we heat organic compound in presence of concentrated sulfuric acid and little copper sulfate, which acts as a catalyst. Boil organic compound with concentrated sulfuric acid in presence of a small amount of copper sulfate, which acts as a catalyst. Then all the nitrogen present in the organic compound will transform into ammonium sulfate. Under these conditions, all the nitrogen present in the organic compound will get transformed into ammonium sulfate when you boil organic compound with excess of concentrated sulfuric acid. Now, the next thing you should do is add alkali, excess of sodium hydroxide, and all the ammonium sulfate will give ammonia gas. Ammonium sulfate, which is formed as a result of this reaction, is treated with excess of sodium hydroxide. All the ammonium sulfate will decompose to give ammonia gas. Ammonia gas is then made to bubble into sulfuric acid. Here, this should be a known excess of sulfuric acid. We take a known excess of sulfuric acid and allow all the ammonia to bubble into that sulfuric acid. It will become ammonium sulfate once again, and you will have unused sulfuric acid. Because you have taken an excess of sulfuric acid, at the end you will have unused sulfuric acid left out after bubbling all the ammonia gas. Now, it is a matter of finding out how much sulfuric acid is unused in this reaction. This can be achieved by titrating the mixture with a standard sodium hydroxide solution. This is the unused sulfuric acid. You will have to make use of standard solution of sodium hydroxide. That means a solution of known concentration. The reaction is called as titration. It is a case of back titration. So, the ammonia gas is made to pass into sulfuric acid, known excess of sulfuric acid, and the left out sulfuric acid is estimated by back titrating it with standard sodium hydroxide. Now, in this experiment, number of equivalents of sulfuric acid, number of equivalents of sulfuric acid is equal to number of equivalents of ammonia plus number of equivalents of NaOH. In the experiment, you will know how much sodium hydroxide is consumed. From that, you can know equivalents of sodium hydroxide. And in the experiment, you have taken known excess of sulfuric acid. So, E sulfuric acid is also known to you. From this, you can find out number of equivalents of ammonia which is produced in the experiment. The difference between this and this will give number of equivalents of ammonia produced in the experiment. From the number of equivalents of ammonia, you can find out mass of ammonia or mass of nitrogen, and from the mass of nitrogen and mass of organic compound, you can find out percentage of nitrogen. But then I'll show you the calculation part in a short while from now, but I want to give you some exceptions to this. Try to realize that we are not using any reducing agent in this experiment, whereas here oxidation state of nitrogen is -3. It's the minimum oxidation state for nitrogen, and remember, we are not using any reducing agent. So that means the original oxidation state of the organic of nitrogen in the organic compound also must be -3, because if it is -3, it continues to remain -3 as we are not using any reducing agent. So one thing becomes very clear here, that any organic compound in which nitrogen is in its -3 oxidation state only can give this type of reaction. That means this estimation works well if nitrogen in the organic compound is in -3 oxidation state. For example, nitro compounds or nitroso compounds or diazonium salts or azo compounds, in these compounds nitrogen is not in its -3 state. So such compounds do not for such compounds this method is not applicable. Okay. In the original compound, nitrogen has to be in its -3 state. Apart from this, try remembering this fact also. This will not work well for those compounds if nitrogen is a part of heterocyclic system, because in such a situation, to remove nitrogen, higher activation energy is required, as it requires breaking of more than one bond at a time. It requires high activation energy. So the temperature to which you can heat this substance is up to the boiling point of sulfuric acid. You cannot go beyond that. So activation energy requirement is not met. So this will not work for compounds in which nitrogen is a part of heterocyclic system. It will not work for compounds where nitrogen have an oxidation state other than -3. That is the limitation of Geldahl's method. So in this way, Dumas method is better than Geldahl's method. There are no exceptions for Dumas method. Most of the organic compounds, almost all the organic compounds, any nitrogen is present in such a compound can be estimated using Dumas method. Geldahl's method is for limited use. I am going to show you calculation part after this. Let's look at the calculation part of Geldahl's method. Let mass of organic compound be m grams. We take a known mass of organic compound. So we already said that the number of equivalents of ammonia formed in the process is nothing but the difference in the number of equivalents of sulfuric acid and number of equivalents of sodium hydroxide. So from the number of equivalents of ammonia, we can arrive at the mass of ammonia. Mass of ammonia equals to number of equivalents of ammonia into 17. That is the gram molar mass of ammonia, which is same as gram equivalent mass, because its n factor here is taken as 1. Now mass of nitrogen is nothing but number of equivalents of ammonia into 14, because this is the atomic mass of nitrogen. Now from the mass of nitrogen and the mass of organic compound, it is possible to find out percentage of nitrogen using this type of formula. Number 3 in the list is estimation of halogen. Estimation of halogen in the organic compound. In this experiment, organic compound is boiled with concentrated nitric acid and in presence of silver nitrate. All the halogen present in the organic compound transforms into AgX, which appears as a precipitate. This is filtered, washed, dried and weighed. From the weight of silver halide, we can arrive at the weight of halogen. We start with known mass of organic compound. Known mass of organic compound. So mass of halogen by mass of organic compound into 100 gives percentage of halogen. Percentage X is equal to weight of AgX. Look at the calculation part of it. Let us assume that the mass of organic compound we take is m grams. Let us assume that the mass of AgX formed in the experiment is m1 grams. Then the mass of halogen present in m1 grams of silver halide is m1 into atomic mass of X. See, if the halogen is chlorine, you take it as 35.5. So, m1 into atomic mass of X divided by molecular mass of AgX. That gives the mass of halogen present in m1 grams of silver halide. Now, from the mass of halogen and the mass of organic compound, it is possible to get the percentage of halogen. It is equal to atomic mass of halogen into m1. m1 is nothing but mass of silver halide into 100 divided by molecular mass of AgX into mass of compound. Actually, this part of it is nothing but mass of halogen. This is mass of organic compound into 100. That gives percentage of halogen in the organic compound. So, it is a very simple technique. Boil the organic compound in a mixture of concentrated nitric acid and silver nitrate. All the halogen present in the organic compound will become AgX. This is recovered by filtration, and then this is the calculation. The next one is estimation of sulfur in the organic compound. Here, organic compound is heated in presence of sodium peroxide. Sodium peroxide here being used as an oxidizing agent. All the sulfur present in the organic compound will become sulfate and appears as sodium sulfate. Then we add barium chloride excess. Then you get a precipitate of BaSO4. This is filtered. It is filtered, washed, dried and weighed. From the weight of BaSO4, it is possible to calculate percentage of sulfur. I am going to show you the calculation part. First, you look at it once again. Organic compound containing sulfur. It is heated in presence of sodium peroxide, which is being used as an oxidizing agent. All the sulfur will get oxidized to sulfate and it appears as sodium sulfate salt. This is then mixed with excess of barium chloride, when all the sulfate will get precipitated as barium sulfate. So, it is now just a matter of filtration. In the residue, you have BaSO4, wash it thoroughly to remove all the soluble impurities, and then dry it and then find out the mass of BaSO4 formed in the experiment. From that, you can arrive at the mass of sulfur. You always start with a known mass of organic compound, and I am going to now show you the calculation part. Look at the calculation part. Let us assume that the mass of organic compound taken initially is m grams. This is the mass of barium sulfate which is formed in the experiment, m1 grams. The mass of sulfur present in m1 grams, see, this is the gram molar mass of barium sulfate. So, 233 grams of barium sulfate contains 32 grams of sulfur. So, the mass of sulfur present in m1 grams can be given by 32 m1 by 233 grams. This is the mass of sulfur. So, now it becomes very simple. Mass of sulfur divided by mass of organic compound into 100 gives percentage of sulfur. So, this part of it, 32 m1 by 233, that is nothing but mass of sulfur. This m is the mass of organic compound into 100, that gives percentage of sulfur. This is how it is obtained. m1 is the mass of BaSO4 which is formed in the reaction, and m is the mass of organic compound taken initially. The last one, estimation of phosphorus. Here, organic compound is boiled with fuming nitric acid. Organic compound is boiled with fuming nitric acid, when all the phosphorus present in the organic compound changes to phosphoric acid, and then you add a ammonia solution and ammonium molybdate mixture into this, when all this will get precipitated as ammonium phosphomolybdate. This you are already aware, ammonium phosphomolybdate. Now, this is filtered and then dried and weighed. Let us assume that the mass of organic compound is m grams, mass of ammonium phosphomolybdate, let us assume it as m1 grams. Now, the mass of phosphorus which is present in m1 grams of this is given by this 31 m1 by 1877 grams. 31 corresponds to atomic mass of phosphorus, whereas 1877 corresponds to gram molar mass of ammonium phosphomolybdate. Now, from this you can find out percentage of phosphorus. This is mass of phosphorus divided by mass of organic compound into 100, that gives percentage of phosphorus. So, with this we have come to an end of quantitative analysis of organic compounds. We have done qualitative and quantitative analysis. Then in the next part we will be talking about some important methods of purification of organic compounds.